When it comes to acyl substitution reactions, we can do acyl substitution reactions with a variety of different functional groups. In many cases, the easiest one to work with is an acid chloride. An acid chloride being a carbonyl with a chloride attached. And this ends up being a very, very good electrophile for this type of reaction because of the very good leaving group we have in the chloride. The negative of acid chlorides is that many of them are highly unstable. And that comes from the fact that, again, they are so reactive. That being said, it's typically something that you can make right before you decide to use it. We don't find acid chlorides naturally. They're too reactive. They're purely used in organic synthesis. But fortunately not terribly difficult to make. And as we said, should you need one, relatively easy to synthesize and then use. So to make one, you start with a carboxylic acid and add SOCl2, known as thionyl chloride, to it. And in a single reaction, you can convert that OH group into a chloride, which you can then use for further steps in synthesis. So how does this work mechanistically? So the thionyl chloride looks in some ways like a carbonyl, but with a sulfur where the carbon would be. That sulfur is bonded to 3 highly electronegative elements, oxygen and the 2 chlorines, and so that sulfur is a very good electrophile. So the carboxylic acid will attack the sulfur, and just like with nucleophilic attack on a carbonyl, that'll push these pi electrons up onto the oxygen. The next step is also very much like something you'd see in an acyl substitution reaction. If you think about acyl substitution reactions, the first step is you attack the carbonyl, make a tetrahedral intermediate. Tetrahedral intermediate breaks down, kicking out a leaving group. So while this isn't exactly the same, we're dealing with sulfur here, not carbon. The next step does look very similar. Oxygen comes back down with its electrons, reforms a double bond, kicks out chlorine. All right, at some point, we're going to lose this hydrogen on the positively charged oxygen. And so now we're ready for the actual acyl substitution that needs to take place to get this chlorine where we need it. And as is the case with many reactions where we are trying to get rid of oxygen, the entire purpose of what we've been doing here is to make that OH, which is a very mediocre leaving group, and convert it into a good leaving group. So that chloride that we kicked out in a previous step will now initiate nucleophilic attack onto the carbonyl. As with any acyl substitution reaction, that's attack on the carbonyl, shift the electrons up onto oxygen to make a tetrahedral intermediate. And then that tetrahedral intermediate breaks down by reformation of the carbonyl and kicking out of the leaving group, which then falls apart to give us our product. So our product here is our acid chloride, which we can then use for further synthesis. And this reaction is helped driven forward by the release of sulfur dioxide, which, as a gas, will make the reaction irreversible.